is the first video for AP Calculus where we're going to recap everything we've been discussing thus far in regards to area between a curve and the x-axis. We're also going to add in a few new things that we have yet to discuss in all of our little activities we've been doing. All right, so first thing we're going to discuss are LRAM, MRAM, and RRAM, which we have been doing by hand so far. We will talk about how to do these on a calculator. So we're going to look at the function y equals 5 minus 4 sine of x over 2 in the window, and we're not real worried about the window, from 0 to 3, 0 to 5. So we want to estimate the area under the curve from x equals 0 to x equals 3 using the DrawRec program that you have now been provided on your calculator. And then we've got the chart here where we're going to organize it. So I want you to go to your calculator, and if you press the program menu, it is underneath the stat menu, then you should have a DrawRec program there. You may have the other program that you see there as well, but that's not the one we're talking about today. We're talking about the DrawRec program. So you're going to choose that program, and then you're going to hit enter, and it's going to take you to the title screen. Yours may look nicer than mine. I don't know why, but for some reason it crunches it up on this calculator. But it doesn't matter. All you're going to do is hit enter, and then it's going to take you to the menu for this program. Pretty much as long as you can follow directions, then you can use this program pretty simply. You're just going to go down the menu in order to do your problem. So we're going to start with step 1, which is to enter in the function. So our function was 5 minus 4 sine of x divided by 2. And you are going to want to make sure that you're in radian mode for this. So if you're not sure if you are, you want to quit out of this program real quick. So just press second quit, and then go to the mode and make sure that you're in radians. And then come back to here. So if you need to pause the video for a minute while you do that, then do that. All right, so then once you've got the function entered in, you hit enter. And then we go to step 2, which is to enter in the boundaries. So this wanted us to go from x equals 0 to x equals 3. And then you'll notice your calculator's thinking, and it will actually draw it for you in the perfect window that you need. So you don't have to format your window to make it the right size, anything. And if you have a color calculator like mine, it's great because you can also see the different color that they use for the boundaries here from 0 to 3. Once you see the graph, then we're going to go back to the menu. Now we're on step 3 for the number of partitions. So that's how many sub-intervals that we're using. Well, if you look at the table that we're filling in there on your notes, we're going to start with 5 rectangles. So partitions would be 5. At that point, it's really up to you whether you do step 4, 5, or 6. And it may just depend on the problem. The problem may only need you to find one of those 3. This particular one that we're doing, though, with the table, we're going to do all 3 of them. So I'm going to start with number 4. This is the coolest part of the program. It draws it. So that's my LRAM picture right there for the interval from 0 to 3. You can look at that and you can tell already that this LRAM is going to be an overestimate because the rectangles cover up more space than the little orangey curve does there. So then once you see the picture, then you hit enter, and then it tells you what the amount is. So you'll want to write that in on your chart. Then we go back to our menu. We can do the midpoint. That looks pretty cool. I can tell that's probably going to be pretty close to accurate because the amount of extra rectangle kind of covers up the amount of uncovered area under the curve. And so I have that I can put in my chart. And then lastly, the right endpoint, which I can definitely tell is an underestimate, and its amount. So then you can fill all 3 of those into your table that you have in your notes there. So now the next thing I want to do is I want to do it for 10 rectangles. I'm still using the same function and the same boundaries. The only thing that's changing now is the number of partitions I'm using. So I'm going to jump now straight to step 3 and change my partitions to 10. And then you could do left, midpoint, and right endpoint. So there's my left endpoint, hit enter, and there's the amount. So I want you at this point to pause the video, and I want you to take the time to fill in the remaining boxes in your chart. And I'll go ahead and tell you 25 and 50 are going to take a little bit, so you're going to have to let it sit there and think it through to put the answers in. So don't get frustrated if it doesn't immediately spit the answer out to you. All right, so pause the video right now. All right, so there you see I have completely filled in my chart. Now, I noticed a few things. First off, the LRAM estimate started off high and got lower, whereas RRAM started off low and got higher. MRAM also got higher, but not by very much, because hopefully, as we've now kind of figured out, MRAM tends to be the most accurate, so it's going to stay the most consistent. And then also, if I look across that bottom row with 50 subintervals, those three are the closest together, the closest to being equal to each other. So if I was going to look at all the information in this table now and try to make an estimate for the exact area from 0 to 3 of 5 minus 4 sine of x over 2, I would probably say it's about 7.566. And I'm going to show you in just a minute how we could find that exact value on the calculator to see how accurate our estimate actually is. So you notice that the more rectangles that we do, the more accurate our estimate becomes. And eventually, if I had done 100 rectangles or 1,000 rectangles or 10,000 rectangles, it really would not have mattered very much whether I was using left end points, midpoints, or right end points, because the more rectangles you use, the more accurate your estimate is, regardless of which of the three ways that you're using. So the idea in a perfect world is that we would use an infinite number of rectangles and add together the sum of their areas, and that would give us the exact area under the curve. Now, in the real world, however, we can't do an infinite number of rectangles and add their areas together. Even doing 50 rectangles isn't really something that we want to have to do by hand, but we can ask our calculator to do it. If I asked my calculator to do an infinite number of rectangles, it would crash. Like, I would never get an answer out of it. But the whole theory of it being the sum of an infinite number of rectangles kind of translates from the limit concept to integral notation. So this sigma notation here, that means the sum of. So what we're doing is we're doing the sum of f of basically the function, so that would be our y values or our height, times the change in x, delta x. Well, that would be the width of each base rectangle. So you're doing base times height, which is area of the rectangle, and then you're summing those together. Well, the goal is to do it from the sum from one rectangle to n rectangles, but n is approaching infinity. So we're trying to use an infinite number of areas of rectangles and adding those together. But rather than always writing our integral notation with that long limit notation like that, they created an integral sign like this. And our boundaries go from A to B, so that would be from the beginning to the ending of our interval. And then notice that inside the integral, it's kind of the same concept of what we had here for h and b. Instead of f of c sub k, it became f of x for whatever the function is. And then instead of delta x to represent the change in x, we use dx to represent the change in x. So, and then underneath here, you can kind of see what all those different things are called. You get your integral sign, you've got your upper and lower limits of integration, the a and the b there. The function that's inside the integral, your f of x, that's called the integrand. The dx tells us what variable we're integrating with respect to. That could possibly be a y or a t or something else, but usually it's a dx. And the way we read it is we say the integral of f from a to b. And then the answer you get is what you get when you have actually evaluated the integral there. So for example, if I had this expression, and let's say I'm going to add boundaries here on 1 to 5. If they gave me this in limit notation and asked me to write it in terms of an integral, well, seeing the limit as n goes to infinity with that sum, that's how I know that it's an integral. The boundaries that I just put in there, those are my a and my b. And then essentially all I do is I go through the rest of the expression. Everywhere that there's an m sub k, that's going to get replaced with an x. And then just remember, instead of delta x, you put dx at the end. That's the only difference to the notation. We hardly ever see the limit notation, but I want you to be familiar with it if you ever do see it. Now, the whole concept of the integral that we've been studying is the fact that a value of an integral from a to b represents area under a curve, kind of. The difference is that area, as you're used to with area measurements since elementary school, is that it's always a positive amount. However, it is possible for an integral to be a negative amount. Like this picture that I'm looking at right now for cosine of x, if I look at it from pi over 2 to 3 pi over 2, that graph is below the x-axis. So its integral value from pi over 2 to 3 pi over 2 would be a negative amount. But if I was asking you for the area from pi over 2 to 3 pi over 2, you would give me a positive amount for that answer. So for example, if I was wanting to algebraically find this area here, I would take the negative integral from pi over 2 to 3 pi over 2 of cosine of x. So what we've learned from integrals is that basically whatever's in here is our integrand. That's the derivative. So we ask ourselves, what is cosine of x the derivative of? Well, it's the derivative of sine of x. And then we have our boundaries from pi over 2 to 3 pi over 2. So then we would evaluate, we always substitute in the upper boundary first, minus the lower boundary. This is how you evaluate an integral by hand. So the sine of 3 pi over 2 is negative 1. The sine of positive 2 is positive 1. So if all I was doing was finding the integral would be negative 2. However, the area would need to be the opposite of that because it can never be negative. So the integral from pi over 2 to 3 pi over 2 is negative 2. The area is positive 2. Okay? And this picture here kind of explains that too, even if you were doing it with rectangles. Sometimes the amount of positive area balances out the amount of negative area, in which case you end up with an integral value of possibly 0, which is what would happen here in this picture. But the area answer would not be a 0 amount. Okay, so the last thing is integrals on a calculator. So there's two ways that it could possibly look depending on which operating system that you have on your calculator. So I want you to go back to your calculator screen. And if you're still in the program, then you'll just need to hit 7 and quit out of that program. Now I'll tell you this, when you go to graph something now in your y equals, it may look funky on the graph or you may see the title screen on the graph. To fix that, all you have to do is press the zoom 6 button and it makes any random weird things go away. So integrals on the calculator, you're going to press math 9 and you get your integral symbol. This is if you have an updated operating system. If you have an older operating system, then it looks like how I have it typed on your paper there, and you just want to make sure to type things in the correct order. So I'm actually going to do the one that we put into our draw rec program to see how accurate our estimate of 7.566 really is. So I'm going to do 5 minus 4 sine of x divided by 2. Close that. Okay. And then at the end, I'm going to put a dx. Maybe, if it'll type. There you go. And then we're going to hit enter. So we came up with 7.566 as our MRAM estimate with 50 rectangles. And look what we got for the exact area under the curve. So if I actually used an infinite number of rectangles, I would get 7.566. There you go. So that shows you how accurate it is. All right, so that's where we're going to end the first video for the area recap. And then the second video is actually going to talk about some things that we haven't really quite discussed in class and introduce some new stuff to us.